welcome to Best Practices for Text on Android. My name is Clara Bayarri, and I'm a text lead on the Android Toolkit team.
I'm Florina Muntenescu, and I'm an Android developer advocate.
Siyamed Sinir, text lead for Android Text.
So why are we giving a talk about text? Well, it turns out text is a major part of your app. It's part of your design, it's part of your branding, it's part of who you are, and it is the major thing that your users will be consuming. It is front, the first thing that your users will read, and the thing that will mostly affect readability, accessibility, usability, all of that. On top of that, the Android tech stack is responsible for emoji, which we all love. But all of this obviously comes at a cost. So there's a bunch of performance implications related to text that we want you to be aware of. So today, we're going to go through a bunch of best practices and things that you should know. Before we can do that, let's talk a bit about the architecture. We want to explain how the tech stack is fitted within Android so that you can better then understand what we're going to talk about later. The tech stack on Android is split into two parts. There's Java code, and then there's native or C++ code. At the very top of the Java layer, you will find the thing that you're probably most familiar with, which is text view and edit text. These are widgets that provide text functionality out of the box and do everything for you. If you have custom views where you don't want to use our widget, then you're probably using the second layer, which is layout, paint, and canvas. This classes on Java will help you lay out text and render it without actually using our widget. Once we get into the native part, the very first layer is a library we call Minikin. Minikin helps us do word measurement, line breaking, and hyphenation. And it is our first point of contact with C++. Below that, there's a bunch of libraries we use to help us. ICU, which deals with Unicode. Harfbuzz, which does text shaping for us. FreeType, which generates bitmaps for all of the glyphs. And finally, Skia, which is our graphics engine. Today, we're going to focus on the top three, as these are the layers that the Android team owns and the one we can provide most best practices and hints into.
Minikin lies at the core of Android tech stack and is implemented in C++. Its main responsibilities are text layout, measurement, and line breaking. It is important to understand what parts are implemented in Minikin versus Java, as that defines which features we can backport using support library, which doesn't allow native code. Let's start with text measurement. If you provide a string like this to Minikin, first it has to identify the glyphs. Glyph is a representation of a character, and you can think of it as the image to be drawn. However, the character to glyph matching is not always one-to-one. Here we have three letters, FFI, matching to a single glyph. Glyphs can also be found in different fonts, which is the case with the Japanese character in the example. This is called the font fallback chain. Once all the glyphs are identified, the system can position them together to have the final look. However, at this point, positioning is not always putting the glyphs side by side, which is the case with the letter E and acute accent. If you provide a longer string, Minikin first divides it into words. And for each word, it does the measurement. The result of this measurement is added into a cache, so that if the system comes across with the same word again, it can raise the computed value. This is a system-wide LRU cache and has a fixed size of 5,000 items. When the string is wider than the array it has to fit in, Minikin has to do a line break. In the simplest case, this is putting the boxes side by side until the boundary is reached, and then moving to the next line. The behavior is controlled with the break strategy attribute. And if we were to switch from simple to balanced here, Minikin will distribute the words among the lines to have better text alignment. The default value is high quality, which is very similar to balanced, except a few subtle differences, one of them being hyphenation for the last line. Hyphenation improves the alignment of the text and the use of white space. And it gets more and more important as the line width gets shorter. However, it comes with a cost. The cost arises because now the system has to measure more words, and it has to compare more configurations for an optimum solution. Up to Android P, enabling hyphenation is 2.5 times more expensive than the disabled state. On Android P, we improved the simple break strategy case. However, the default configuration still has the same cost. Another thing that affects hyphenation is the locale. In this example, we have a device in the English locale and two example strings. One of them is not hyphenated correctly, and the other one did not choose the right glyph for the Japanese text. This will mostly happen for dynamically loaded text, such as the strings loaded from network. And it happens because the system is not aware of the languages of those strings. To fix this, we have to tell the system about the language using the setTextLocale function. If the string contains multiple languages, you can use local span to mark different parts of the word string. However, keep in mind that the number of local spans affects the performance of the text layout.
One of the most common tasks when working with text is text styling. So usually we would start working with the text view attributes and set the text size, text color, and font. So we call this a single style because all of these attributes affect the entire text from the text view. But usually, for the designers, this is not enough. And they will want to style specifically one word or one paragraph. So what they want is to apply a multiple style to the same text block. So in order to achieve this in Android, we work with spans. Spans are markup objects that can be attached to text from a start to an end index. And spans can be categorized into character and paragraph spans, depending on whether they apply to only a few characters or to entire paragraphs. And then character spans can be split into appearance and metric affecting. And the difference between them lies in the method that needs to be called on the text view in order to render the side. So appearance affecting spans require a redraw to be called, whereas metric affecting spans require both a remeasure and a redraw. Let's see an example. So let's say that we need to style a code block. So in order to do this, first we would change the background color. So for this, we would use a background color span. This doesn't change the metric of the text. So this means this is an appearance affecting span. But we also need to change the font. So for this, we would use a typeface span. But because fonts also change the size of the text, this is a metrics affecting span. To style blocks of text by, for example, changing the layout margin or drawing a bullet in front of the text, we would use a bullet span. So paragraph spans, like the bullet span, have to be attached from the beginning of the paragraph and affect the entire text of the paragraph. The thing is that if you don't attach it from the beginning of the paragraph, well, chances are you'll lose the styling completely. So in the framework, we define a series of interfaces and abstract classes. And under the hood, the framework checks for instances of these classes and then triggers different actions depending on them. But actually, what makes spans so powerful is the fact that they give you access to things like the text paint or the canvas in the case of some paragraph spans. So this means that you can pretty much handle everything you need in terms of text. So first of all, whenever you need a span, check the ones that are available in the framework, because they cover most of the common use cases. OK, but if we go back to our example, we see that the typeface span only gets a typeface starting with Android P. So this means that if we want to support pre-P devices, we will need to create our own custom span. So to do this, we would extend from metric affecting span. And this class gives us access to two methods. To update measure state, which is called when text view on measure is called, and update draw state, which is called when the text view on draw method is called. And both of these methods give us access to the text paint. So then, in the text paint, all we need to do is change the typeface. But if we have the text paint, it means that we can also set the background color. So it means that we can just create one code block span to style our code block. OK, so now we have two different ways of styling our code block. One with composing multiple spans, one from the framework and a custom one, and another way where we're using a custom span. So which one should you use? To help you decide, there's one important piece of information that you need to remember. Only framework spans can be parceled. So there are two common cases when the spans are parceled. First, when we're passing text via intents, or when we're copying text. Independent if we're copying text, for example, from a text view to an edit text in the same activity, or whether we're copying text from one application to another, the text gets to be parceled and unparceled via the clipboard service. So this is what will happen. If we're passing the text with one framework span and one custom span, well, just our framework spans are passed. So this means that we're losing our custom typeface span. But then if we're passing a text with one custom span, then it means that no styling will be kept. So in general, when you're implementing spans and the text gets parceled, consider the behavior you want. Should the style be partially kept or not?
So now that you know about spans, how do we use them in text? Well, the framework provides two key interfaces for this. The first one is spanned. Spanned is for immutable text and immutable markup and declares methods such as getSpans or getSpanStart and getSpanEnd. It lets you query spans but not modify them. If you want to modify them, we have spannable, which has the ability to mutate the markup with methods such as setSpan or removeSpan. Then we have three concrete implementations of these interfaces. The first one is spanString, which implements spanned, and as such has immutable text and immutable markup. Spannable string, which implements spannable, as such has immutable text but mutable markup. And finally, we have a third class which adds mutability to the text, which is spannable string builder. This is what we use internally, for example, for edit text, because it allows you to modify the text and the markup. These last two classes are very different internally. Spannable string holds an array of spans, whereas spannable string builder holds a tree of spans. So these are widely differently implemented. So as a team, we were wondering, well, is the tree more efficient? Maybe there's a case where we want to recommend people to only use spannable string builder all the time because it's more efficient. So we ran tests. The answer is up to 250 spans, they're the same. They basically perform equally, so we recommend you do what makes most semantic sense, which is use spannable string for immutable text, spannable string builder for mutable text. However, after 250 spans, they really do start to diverge, and we recommend you use spannable string builder for all of your cases, just because it is more performant. Out of curiosity, we ran these tests to the limit. Turns out when you have thousands of spans, they really diverge, but we really, really hope this is not a common use case for anyone. Another common thing we see with spans is people trying to check if one span is present within a spannable. And the solution we've seen online uses span.getSpans. So it's something like this. You just query for all the spans of a given type, get an array back, and then just check if the array is empty. This is extremely inefficient. You're going through the entire span looking for all of the instances of that span, collecting them all into an array, and then just checking if that array is empty. There's a better way to do this, which is next span transition. This method checks for the boundaries of spans. So when you ask for the first boundary of a certain span, it will just have to do the work until it finds the first span, and then it can stop. And it won't collect any spans into an array, wasting memory that you shouldn't do.
A frequent task when working with styling text is styling internationalized text. So usually in your resources, you will define the same string in multiple languages. But then you need to highlight one specific word. So here, for example, we want the word text to be bold. But the thing is that the word and where it appears is different in every language. So one easy solution would be to just use HTML tags. But the problem with this is that HTML tags have limited functionality. So if, for example, we want to change the font, well, this is not something that HTML can provide. The solution for this is to use annotation tags. So the annotation tag allows us to set key and value pairs, and then define whatever we need. So here, for example, I'm defining the key font and the value to be the font name. And this is how we would use it in code. So we would get the text from the resources as a spanned string. Then we would get the annotations from the span. We would iterate through them and get the ones that have the key that we're interested in, and then the value. And then we would set the span based on the indices.
We will now look at how text is laid out in the view. Let's assume that you have a text view with some padding applied. When you set the row top, text view will position the image to top of the view after the padding. Get compound padding top function will return you the distance from top of the view to bottom of the image. Setting the drawable padding will add extra spacing between the image and the area that the text will be drawn in. And now get compound padding top will point to this new location. When you set text, text view will create a layout object. Layout is responsible for rendering and measuring text. Here, the boundaries of the layout are highlighted in orange. It will also provide you some more information about the text it contains, such as the baseline top and bottom of the lines. There are 3 layout classes on Android. Boring layout is for single-styled and simple text, which doesn't contain tab, next line, or right to left characters. Dynamic layout is created for editable and selectable text, and for other cases, text we will create a static layout. When you set the gravity, the layout object itself will be positioned in the view. Get total padding top will return the distance from top of the view to the top of the layout. Include font padding. This attribute will add extra spacing to top and bottom of the layout. And the value, the height of this spacing is calculated using the values in the font. The effect is more visible when you use a tall script. In this example, when it is set to false, we see that the text is clipped. Since it only applies, when you set to true, it only applies the spacing to top and bottom of the text, on Android, we will see that lines would overlap. On Android P, we fixed this issue. Now, if the system identifies that the text, the lines will overlap, it will put extra spacing between the lines and will apply this rule to the whole paragraph. To provide an opt-out option, we added an attribute named fallback line spacing, which is by default turned on. A similar attribute that changes the line height is the elegant text height attribute. However, even though it changes the line height, unlike the other attributes, it will not add spacing, but it will actually start using a different font. There are two different fonts defined in the Android font fallback chain, compact and elegant. Setting elegant text height to true will make the system choose the elegant version of the same script if that font exists. Speaking of line height, it is an important attribute for the readability of the text, and you can control it using line spacing extra and multiplier attributes. These attributes will add extra spacing in between the lines, but not the last line. Since developers mentioned us that designers would mostly provide line height as it is, but not as multiplier or extra, on Android P, we added the line height attribute. Two other attributes that we added on Android P in order to bridge the gap between design and implementation are first baseline to top height and last baseline to bottom height. The first one will let you control the distance between the top of the view to the baseline of the first line. And the second one, similarly, will let you control the distance between bottom of the view to the baseline of the last line. Finally, when you set text alignment, the text will be positioned in the layout. Get line left and get line right functions of the layout object will give you information about this positioning relative to the layout boundaries. Now that we know about layout and some important functions, we can answer a frequently asked question on the internet, which is how to implement a rounded background span. This is not doable with spans, but we can implement it, we can draw it ourselves using the layout functions. To do that, first we need to mark our words that we want to draw the background for. Annotation that Florina mentioned is a good option for such a use case. Then we will define our drawables. 3 for the words that start and end on different lines, and 1 for the words that start and end on the same line. We will loop over our annotations to find our words. Then, for each annotation, using the start and end indices, we want to learn the line number, and we can use getLine for offset function of the layout, which will convert a character index into a line number. For the words that start and end on the same line, we also want to learn about the vertical coordinates of the line. We can use getLine top and getLine bottom functions for this. And finally, we want to learn about the horizontal coordinates of the words. And getPrimary horizontal function will convert a character index to a horizontal coordinate relative to the layout boundaries. Now that we know the rectangle that we want to draw in, we can draw our drawable. The other case where words start and end on the different line will have almost exactly the same code, except now it has to identify more rectangles to draw in.
Text view goes through the same 3 phases that any view on Android goes: measure, layout, and draw. Measure is by far the most expensive for text view. Here is where we create the layouts we just talked about, or recreate them if we need to, and where we decide on the width and the height of the view. This is really expensive work. Later, in on layout, we barely do anything, just some scrolling and auto-sizing. And finally, in onDraw, we issue the drawing commands. But measure is really, really expensive, and you need to be very aware of this. It's important to distinguish what causes an onMeasure with what causes an onDraw. As Florina mentioned before, anything that causes the text to change in size or how it needs to be laid out, such as the letter spacing, the typeface, maybe the text size, that will have to trigger an onMeasure, as we need to recalculate that layout. Whereas if you change something that just changes the appearance, but not how we place the text on the screen, such as the text color you're going to paint it in, that only needs to trigger an onDraw, which is much, much cheaper than doing an onMeasure as well. Let's look at these two phases separately. Say we have a text view like this. I've set some text that has several paragraphs. And then I've used spans to style some of the words in it. I've changed the text size. I've changed the colors. Well, the first option to measure your text is there's a method in Paint called measure text. A dead giveaway of this method is it takes a string, not a spannable. So what this will do, Paint just doesn't understand spans. So it will take the text you've given it. It doesn't understand line breaking either. So it will place all of the text as one very long line, ignore all of your spans, and give you the width of that text. The next option is to use getTextBounds, also from Paint. Again, dead giveaway, it takes a string. So it will do exactly the same, no line breaking, no spans. It will place it all together, and it will give you the bounding box of all of your glyphs, which is a width and a height. It's important to notice that these two methods return slightly different values. So textPaint.measureText will return you the next advanced glyph. This is where you will position the next glyph if you were to add another one. Whereas getTextBounds will give you the bounding box of the glyphs you have. And these two values come from different parts of the font, so they may be very different. If we want to improve on this, well, we use layouts. Layout has a static method called getDesiredWidth. What this does is it takes the text you give it, it places each paragraph into one line, and taking into account all of the styling, it measures each of the lines. And then it returns the width of the longest line it has. So it will give you the width of the longest paragraph you've given it. This is useful to know how much your text wants to be before you can restrict it. If you know the width of your view, well, then you actually create a layout object. In this case, we've created a static layout. By having the constrained width you want to fit it in, layouts can actually calculate how to reflow the text and how to make it fit and give you a height in return. So by giving it a width, we can actually calculate the height. On top of that, as Siyamed mentioned before, you will get a lot more information out of your layout object. For each line, it will give you things like the baseline, the line start, the line end, and so on. We've measured the performance of all of these methods next to each other. Measure text is the cheapest. So compared to measure text, you will see that layout getDesiredWidth and Paint getTextBounds are quite cheap to run. They are similar. But once you get into creating a static layout, or once you ask TextView to measure text, that gets more and more expensive. So now that you know what each of these methods do, make sure you use the one that makes sense for your use case. Similarly, we've talked before about the word measure cache and how we measure words once and we place them in a cache. Well, for Paint, when you call measure text on the same word a second time, turns out it only costs us about 3% of the work to return that value, which is a huge gain. So once we have a hit in the cache, it's only 3% of the work. If we measure this in TextView, there you go. OnMeasure takes about 16 to 11% of the work that it did the first time it sees a word. So definitely using that cache is really important for us. So as I said several times now, measurement is really expensive. What can we do about it? Well, in P, we've come up with a new feature called pre-measured text. The idea behind it is we know that in OnMeasure, we need to take all of the glyphs, find them in the font, place them next to each other, and measure all of these words that we will place in the cache. So what pre-measured text does is it takes care of this phase for you, and you can run this in any thread, so that then once you have that pre-calculation, setting it on the text view only takes about 10% of the work that you had to do initially, which is a huge gain. The way this looks in code is we need a bunch of attributes to know how to measure the text. Things like the font you're going to use, the text size. We have a convenience method in TextView that will retrieve all of these for you. It's getTextMetricsParams. You can also build this object yourself if you don't have the TextView you're going to work with yet. And then on a background thread called precomputedText.create. This triggers all of the things we've been talking about. It measures each of the words, it places them in the cache, and it stores all of those values. So this is also useful if you're going to measure more than 5,000 words, as this actually stores all of the values. Then once you have all of this precomputed information, you can go back to the UI thread and set it on your text view. Notice that all of this only makes sense if you know your text beforehand. If you just know your text as you're going to render it, do what we've always done, because you're going to be blocking the UI thread anyway. But if you do know your text beforehand, say you're loading it from the internet or you have an infinite scroll, you can run this, pre-compute all of your text before it needs to be shown on screen. And the gain is literally 90% of the work will be done on the background thread, which is amazing. Mention in support library, we do have a solution. For P, we just run this. Between L and P, we can actually not do exactly the computations that we've done, but we can warm up that cache for you. So that's what we do. And then before L, sadly, we can't do anything, so it's a no-up. But we do have a solution in the support libraries. Another common thing we see related to all of this is very long text. People tend to just say, oh, I've got the text. I'll just set it all on the text view. When you set text on text view, it layouts and, well, it measures all of the words and lays out the entire text you've given it, even if you've given us like an entire book. So this can be a huge performance hit if you're setting very long text that then you're not actually showing on screen because maybe the user never scrolls. A solution to this is to split your text into separate pieces, say, for example, paragraphs, and put them all into a recycler view as different items. Then this way, while the user scrolls, we will start loading the next bits, but we won't actually be triggering a measure in a layout of all of your text. You can also link this to pre-measured text, which I just talked about, and pre-measure all of the background measurement. Then you will have all of that information really, really efficiently. So we've talked about measure. What about draw? Draw is much cheaper, but you also have several options if you're going to draw yourself. Easy one that people tend to say, oh, why don't you just canvas.draw text? That's easy, right? Turns out Canvas does not understand spans or line breaking or any of the things we've been talking about. So similar to the things we were talking about before, it will just draw the text you give it with no styling as one run. Instead, if you have styling or if you want to use line breaking, again, use the layout classes. You can see the recurring theme. All of the layout classes have a draw method that will actually draw on the canvas for you.
OK, I think it's time we actually set the text, but in a performant way. So set text, I think, is the most commonly used method. And it's great for text views that don't change. So when both the text and the markup attached to it are immutable. So under the hood, the text view creates a defensive copy as a span string. So this means that if you're changing the original reference, the text view doesn't update. But what if we want to mutate the spans later? Or to do this, we would set the text using buffer type spannable. So under the hood, the text view will create a copy of it, but as a spannable. So this means that while the text is immutable, the spans are mutable. So then once what we can do here is we can get the text as a spannable, and then we can add or remove spans to it. And I know that you'll be tempted to call set text again, but you don't need to do this anymore. Because text view has an on-span change listener, and it automatically knows when something was added or removed, and the text will just be displayed. But what if you want to change an internal property of the span? So in our case, we want to change that typeface in our custom typeface span. Well, in this case, the text view doesn't know what changed, and it doesn't know that it needs to do something. So we need to tell it. And we would do this with either request layout or invalidate, depending on what kind of attribute has changed. So if you change the measure affecting attribute and the text view needs to remeasure and then redraw, you would call request layout. But if you just changed an appearance affecting attribute, then you just need to invalidate and call redraw. But what if you also want to mutate the text? So if we look at the code, we see that under the hood, the text view creates a copy using a spannable factory. So it has a default spannable factory implementation. But we can implement our own. And then instead of creating a copy of it, we will just return the same reference to the object in case the object is a spannable. And then we just set that spannable factory to the text view. So this is specifically important if you're using styled text inside the recycler view, because like this, you avoid creating copies inside the recycler view, saving both CPU time and memory allocation. So in the recycler view, this is how you would use it. In the view holder, you would set the spannable factory you've just created, and then in the onBind view holder, make sure you're also setting the buffer type as spannable when you're setting the text.
Another common thing we see related to recycler view is the use of AutoLink. You might be familiar with like taking a text view and just setting AutoLink to say web to be able to detect URLs within your text and have them automatically linked. Well, what happens under the hood when you do this? Turns out that when you set a text on that text view, first of all, we will create a copy, just like Florina said, and then we run a matcher for a regular expression on your text, and for each match where we find a URL, we will create a URL span and add that to your text. If you do this inside onBind view holder, you're creating copies, and you're running that regular expression every time you're setting text, even if you're showing the same text in each item. So you have a little footer with a link. You're going to be recalculating that for each and every item. So the solution to this is, one, don't use AutoLink in your XML, because that automatically triggers all of the process. Instead, first of all, create a spannable copy of your string, and run either Linkify or Linkify compat to be able to find all those links beforehand. So you pre-calculate all of it. Then in onBind view holder, you simply have to set the text. And if you use Florina's trick of using buffer type spannable, you will be avoiding all of those copies and avoiding all of this extra computation. Related to this, in general, we want to discourage everyone from using AutoLink map. All of the other options in AutoLink use regular expressions and are easy to run. However, map actually spins off an instance of a web view to find addresses, which is a huge performance hit for your app. So we want to discourage everyone from using map, or all, which includes map. And you might say, well, but I need this, and you're taking it away. What do I do? Coming to the rescue is Smart Linkify. You might remember last year, we presented Smart Selection in O, where we used machine learning to detect entities when you were trying to select text. Where this year, we've taken those same machine learning models that detect entities and applied them to Linkify. This way, we can do a much better accuracy at detecting all of the entities, and we can detect new types. So on top of phone numbers, URLs, and addresses like we were doing before, we can do more sophisticated things like flight codes. The way this works in code is you create a text links request with your text, and it can also take some options. Then on a background thread, you call textClassifier.generateLinks. It's very important that you do this on a background thread, as this is loading a machine learning model from disk, so please don't do this on the UI thread. Once it comes back, it has all of the detected entities. You can apply those links to the text. There's a change here between the old Linkify and this. The old Linkify used to generate a URL span that when you clicked, it would just go through the link. In the case of Smart Linkify, the URL spans that are being added pop up a floating toolbar with smart actions that you can take. So for example, for an address, we might suggest maps. Finally, when you have all of your text ready, you can go back to the UI thread and set that text on the text view. Notice there's a big difference between the old Linkify and the new Linkify, in that the old one was synchronous, and this is asynchronous. We understand this is a huge difference, but it is the way that we can use machine learning to really enhance how we detect entities, and the accuracy on the new models is really, really much better. And since I'm talking about new features, let me introduce our last new feature for P, which is magnifier. A lot of people tell us that selecting text is really hard, and placing the cursor where you want is a really hard task. So magnifier shows a zoomed-in version of where you are touching with your finger to help you place the cursor in the correct position. We've implemented this by default in TextView, EditText, and in WebView and Chrome, so you don't have to do any work if you're using the default widgets. However, if you're doing your own custom widgets and you want to implement this yourself, there's a very easy API to use there. You could do something like this, like just take your untouch event, and whenever the finger goes down, show the magnifier. Whenever the finger goes up, dismiss the magnifier. This creates an effect where the magnifier kind of follows your finger around the screen. This is not the final UX we've gone for. We kind of snap to the lines. We will publish guidelines on the final UX we've come up with, but it is very easy to use. So I hope today we've presented a bunch of tips and tricks. We've shown you what text is under the hood on Android, and we've provided more information on how to style your text so that you can take all of this back to your apps and build beautiful, more performant apps.